You're listening to Worth Electronics What's Up radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and our Worth Electronic technical specialists. We're going to shine a light on our topics like energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with the Worth Electronics What's Up podcast. Ethernet is rapidly gaining adoption as the dominant networking method for an increasing number of applications outside of IT. For example, industrial applications like process control, automation, and even industrial robots. The problem, however, is the operating environment. Now, unlike the IT industry, industrial facilities are typically full of motor-driven automation and process control equipment. With potentially long cable runs, the risk of interference from high current spikes and transients is significant. Today, we are going to investigate how Industry 4.0 is leading the deployment of industrial Ethernet connectivity. We'll also discuss how the differences in the operating environment between IT and OT, that's operational technology, now require a more robust and reliable physical layer. As industrial initiatives such as Industry 4.0 and the broader Industrial Internet of Things, that's IIoT, gather momentum, the need to manage this technology architecture across such contrasting automation landscape is becoming more essential. So to achieve a single, seamless, and converged network, any new network topology must support the legacy infrastructure existing in most factories and production facilities. There's also a growing need for deterministic behavior across the whole industrial system, not just for isolated individual items of plant. Ethernet provides a flexible, scalable, and well-supported networking protocol upon which to establish an industrial variant. As a result, several industrial Ethernet protocols now exist that use modified media access control, or MAC, layers to incorporate support for legacy networking protocols, low latency, and deterministic features. Industry support for further developing the Ethernet protocol for industrial applications has really led to the creation of the time-sensitive networking IEEE 802.1 Ethernet extension. Now, unlike the conventional use of Ethernet in offices and data centers, the industrial domain presents several challenges, particularly concerning the physical layer, or the PHY. The PHY is responsible for converting information from the data link layer into electrical signals to send and receive across the physical network cabling. The PHY of the network IEEE 802.3 standard stipulates signaling speeds, network topologies, and electric signal specifications. So this means the signals transmitted and received across the network will encounter higher levels of electrical noise generated by a variety of those typical industrial applications, such as switchgear, production equipment, and electric motors. High voltage and high current surges produce radiated and conducted electromagnetic interference in the form of spikes and transients. In larger production facilities where long cable runs, perhaps even up to 100 meters, and equipment producing electromagnetic emissions, such unwanted interference is likely to become induced on the network cables. All equipment connected to the network needs a higher degree of electromagnetic immunity, or EMI, designed inside. Another electrical disturbance comes from electrostatic discharges, or ESD. ESD can occur during installation or maintenance of equipment, but it's also found in production environments with fast-moving materials such as conveyor belts or other production lines. The likelihood of these electrical conditions occurring in an office or data center environment is a lot lower. However, when designing industrial systems, there is a need for extra precautions to mitigate the effects of EMC and ESD. Equipment designed for industrial applications must comply with several internationally recognized EMC and ESD standards. They also need to meet the practical needs of the environment in which it's installed. The standards referred to include the following EN and IEC standards: 61000-4-5 for surges, 61000-4-4 for electrical fast transients, 61000-4-2 for ESD, and 61000-4-6 for conducted immunity. Also, not only should the equipment be protected from EMI and ESD, but it should also not produce any interference emissions from itself. This requirement is covered by standard EN/IEC 55032 for radiated and conducted emissions compatibility, or EMC. For the equipment manufacturer, certification against the standards listed is a time-consuming and a very costly process. Selecting components that already comply with EMC and ESD standards could save considerable amounts of time and speed getting the new product to market. Another aspect of PHY design and operation is thermal management. As network speeds increase, especially with gigabit data rates becoming the new norm, the amount of supporting circuitry also increases. Factory floor space is always at a premium, with a minimum amount of space available for control cabinets. These cabinets are under pressure to squeeze more and more functions into a limited area, increasing the need for low power consumption, high energy efficiency applications. Equipment mounted closer to the machinery also requires thermal design considerations. Sealing inside a water-resistant enclosure places several design constraints in the way heat can be dissipated, while maintaining intrinsic protection against fluids and also dust. Again, components that already have energy-efficient and low-power characteristics make the mechanical and electrical design a lot simpler, and in the long run, could be a lot cheaper. Most PHYs used in consumer and office equipment have an operating temperature range of 0 to 70 degrees Celsius. Within a space-constrained design, the ambient temperature may well exceed this, so this means the industrial Ethernet PHY should meet the industrial temperature range, which is negative 40 degrees to positive 105 degrees Celsius. Two other essential selection criteria of a PHY used in industrial Ethernet applications are latency and data rate scalability. Now, latency has two considerations. First, latency has to be as low as possible to maintain low levels of network cycle time, which is the time to read and collect information from all attached network devices. Second, is to offer a latency time that is predictable for time-sensitive, real-time applications. Since most industrial Ethernet deployments use a line and ring topology, each connected device requires two ports, data in and data out. These add to both pass-through latency and power consumption. Data rate scalability future-proofs the PHY against new data standards. Industrial automation equipment typically requires an in-service life of around 15 to 25 years. During that time, devices using new standards such as the low power, low data rate PHY standard IEEE 802.3 CG/10BASE-T-T1L will see deployment. High bandwidth advancements will add to the list of requirements for the PHY. One example of a robust Ethernet PHY specifically designed for operating in the harsh industrial environment and with an extended temperature operation of up to 105 degrees Celsius is Analog Devices ADIN 1300. This low-power, energy-efficient 110,000 gigabit single-port PHY actually consumes less than 350 milliwatts when operating in 1000 base T mode and conforms to all the industrial EMC and ESD standards that we talked about earlier. Latency in 1000 base T operations is 68 nanoseconds in transmit and 226 nanoseconds during receive. The ADIN 1300 meets all the requirements of the EtherCAT Industrial Ethernet Protocol. Figure 4 of this podcast illustrates the functional block diagram of a simple application. When designing a PHY circuit, the selection of the magnetics needs very careful attention. Achieving galvanic isolation between the host application and the network protects both sides against faults and transients, and this is an essential part of any Ethernet design. IEEE 802.3 standards, referring to IEC 60950, require a minimum isolation voltage of either 1500 RMS voltage or 2250 DC voltage for 60 seconds. A specially designed transformer, such as Worth Electronics' Super Tiny Signal Transformer, or the WE-STST, is ideal for use with the ADIN 1300 PHY. This compact, discrete device measures 4.7 by 3.22 by 2.9 millimeters, allowing a high level of design flexibility and making good use of available space on the PCB. The automated production of this transformer minimizes the deviation or variability between parts when compared to hand-wound ring cores. In conclusion, when designing an industrial Ethernet application, the selection of the PHY requires careful attention. The PHY must be capable of working reliably in environments subject to extreme electrical noise. It must also adhere to ESD and EMC specifications. Also, as with many space-constrained design, the need to operate at extended temperatures is imperative, as is the need for low-power credentials. The analog devices ADIN 1300 and Worth Electronics WE-STST complement each other perfectly in these applications. You can find more information and sample the Super Tiny Signal Transformer WE-STST available at Worth Electronic online. You can also download this application note by clicking the link available in this podcast. You're listening to Worth Electronics' What's Up radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Worth Electronic technical specialists who are going to shine a light on interesting topics such as energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Worth Electronics' What's Up podcast.